morning and happy Diwali to all of you. Today we will discuss some of the special cases. For example, all the filters we have. Kalman filter is not the first filter that we are studying in this course. We have already studied other filters, but Kalman filter is distinguished because it was a time varying filter. Previously our filters were generally time invariant. So an important thing is to understand that does the Kalman filter at all behave like a time invariant filter, which is simple to compute and analyze, and if it does, is it stable? That's any dynamic system, even a Kalman filter is a dynamic system. So one of the important things is to know whether it's stable. Analyzing the stability of linear time varying system is not that simple, but at least we can find out that whether under certain assumptions, at least whether the Kalman filter is going to be stable by analyzing the time invariant version of the filter. We are also going to look at we have derived the filter under certain assumptions like this noise is white, that noise is white. Now in a practical case, it may not be the situation that always these noise sequences are so nicely white, because they may be mainly because they may be coming from a common source, right? So one of the things that is mentioned is that sometimes in aircrafts the sensor which senses its motion, for example red gyros, are mounted on the aircraft or the vehicle. So if there is a disturbance coming on the aircraft because of wind gusts, whatever, that disturbance is firstly affecting its motion. So it can be interpreted as process noise. Secondly, it is also affecting the sensors which are on the aircraft. So therefore, it is also affecting the measurement. So it is also causing measurement noise. And since they are coming from the same source, so they are obviously correlated. So such situations are not uncommon. So we'll have to see that how we are going to tackle the problems when such situations arise. That is, the process and measurement noise becomes correlated, or the process noise sequence and the measurement noise sequence are not fully white. Getting fully white sequences are somewhat idealization. So we'll see how we can make easy transformations so that and get into some equivalent form which again satisfies some assumptions. So as usual, we will obviously we perhaps should not be, need not be, and cannot be very mathematically rigorous in this class. So we'll state a number of results, but we'll intuitively try to see that how these results are arrived at, rather than getting through the equations, which is may not be very interesting, or maybe a bit depressing also. They get so complex. So I have tried to avoid that. If in case you want to find the equations, they are all there in the books. You can go through them. So here we are going to answer. Specifically, these are the questions that we are going to take up. That when does the Kalman filter become linear time invariant? We can say that first we will examine whether is the LTI KF stable, and what if the noise sequences are either autocorrelated, or that means that in each individual noise sequence is not white. By autocorrelated, I mean that the autocorrelation function is not exactly a delta function, or if they are cross correlated, that is, the process and measurement noise sequences are correlated. Okay. So let's take up things one by one. Okay. Put it here. First of all, let us realize that this is the basic Kalman filter equation. You can I have put it in one step ahead prediction form, in the sense that we have measurements up to k and we want to predict k plus 1, and that I have related, that is in this equation I have put both the time update and the measurement update together. If you do a time update, then from k minus 1 you will go to kk. No, if you do a measurement update, then from k minus 1 you will go to kk. Then if you do a time update, then you will go to k plus 1k. So I have put both of them together and I have directly related k given k minus 1 to k plus 1 given k, right. So in that sense, it is like if you call this whole thing as, let us say k dashed plus 1. So if this is called, then this whole thing can be called k dashed, right. So it is like a state equation. This Kalman filter looks like a dynamics, basically a discrete time state equation. So you have x k dash plus 1 is equal to something into x k dashed plus something into another external signal. This something is the state transition matrix of the Kalman, the state matrix of the Kalman filter, right. So this is like A and this is like B. So obviously if you want this filter to be, we are trying to examine that under what conditions is this update time invariant. So obviously you can understand that at least if you want it for arbitrary ABC, then first thing is that the system should be LTI. That is, system should be LTI means that AK is equal to A. There is a state matrix of the system does not change at every time instant. It is a constant thing which we normally consider. So AK is equal to A and CK is equal to C. That is one of the, possibly one of the requirements. Otherwise you will require very in some very peculiar cases of A and C, it may so happen that AK is time varying and CK is time varying and GK is computed in that peculiar way through the Kalman filter, but the whole thing is time invariant. That will be rather rare. I do not know whether it will ever occur, but that it certainly will not hold for arbitrary AKCK. So since we want a result which is applicable for any system, so we will assume that, so the first condition that we require for this system to be linear time invariant, it seems intuitive that we will require that the system itself is linear time invariant. So let us first assume that. So A and C are linear time invariant. Now what is remaining is this G. So if G is time invariant, then the whole equation will become time invariant, correct? So what is, now G contains various things. G of all things, it will contain P, it will contain Q, R, all these things will be contained. So first of all, let us assume that the inputs are also stationary. If the inputs are not stationary, after all the inputs are coming here. So if the inputs are not stationary, this system can be, of course, system can be linear time invariant, but this gain contains these Q and R's. So therefore they won't be stationary. So let us also assume that these signals are stationary, in the sense that they are already assumed to be zero mean, but their covariances depend do not, they are actually constant. Okay. Now if we assume this, then can we say that GK is equal to G for all K? So let us look at the GK equation. First of all, let us understand that this is the GK equation. After making the assumptions that this is the state covariance, I am calling Pk given k minus 1 as Pk. Just both indices are not necessary, so I have removed one. So this is the formula for GK. These are all derived, so you can look up. So you can find out that the problem of determining whether GK is time invariant is the same as the problem of determining whether Pk is time invariant, because if Pk is time invariant, GK is going to be time invariant. In this all other things are time invariant. correct. So basically the problem is to find out whether pk is time invariant. Now how does pk update? So that means that pk should not change with k, it should remain constant. Now pk is actually updated through the Kalman filter. Again there are just like xk, there are two updates, like you first go from pk given k minus 1 to pk given k and then go to pk plus 1 given k. So if you club these two just like I did for x hat, you get an equation like this. These are algebraic. This equation is incidentally known as the matrix Riccati equation. Now if we want that in successive iterations of k the same matrix will remain, that means pk minus 1 is also equal to p, some constant matrix p, and pk is also equal to some constant matrix p, then I will put p on the left hand side and I will put p on the right hand side, obviously. So if there is a steady state solution, if p ever converges, if pk ever does not change with k but remains steady, if this has to happen, then that matrix p must satisfy this equation both on the left and right hand side. That means p will be equal to a p, this equation. In this equation I have just put, in place of pk minus 1 I have put p, in place of pk I have put p, then I get this equation. So if both of them have to remain constant and equal to some matrix p, then that matrix p must satisfy this equation. So this is known as the steady state solution of the matrix Riccati equation. but if it has to, so if it converges, then it will satisfy this equation, that is okay. But then how do we know at all that it will converge? We have not yet known that. You have to follow the line of argument. We want to prove that the Kalman filter equation is LTI. So we have first made assumptions that system is LTI, noise characteristics are LTI. Then we found out that what remains to be proved is that G, or the Kalman gain, is LTI. Coming one step back, we have said that G will be LTI if P is LTI. P does not change with time. We are trying to gradually coming back, and we'll arrive at very nice conditions under which the Kalman filter will become LTI. Then we are saying that when will P be LTI? That is the question. So P will be LTI if P at all converges to some constant matrix. It is true that it must satisfy this matrix Riccati equation if it converges. But the question is, will it converge? So how do you know that? How do you know that something converges? So for example, if you see, for example, this thing. If you are given, let us talk about a number. So if you are given a number which actually increases like this, when can you say that? I mean, how can you argue that it is this sequence of numbers, say one value here, one value here, one value here, this sequence of number is going to converge? How do we argue? We say that first of all, in this sequence, every number, this number is greater than this is greater than this, so it is an ever increasing sequence. But although it is an ever increasing sequence, none of its values will cross, let us say, 1 minus e to the power minus alpha t. This sequence looks like this. As t increases, that is, if you have t1 greater than t2, then you also have 1 minus e to the power minus alpha t1 greater than 1 minus e to the power minus alpha t2. So this function is monotonically increasing with t. How do you know that it converges? Because it is always bounded by 1. Whatever is t, its value can never be more than 1. So it is continuously increasing, but it has a roof. It cannot shoot through the roof, which means that it must stabilize at some point. If it did not stabilize, it would have gone through the roof. So if you can prove that some function has an upper bound, so it cannot increase beyond a certain point, but it is all the time increasing, that will show that it must converge. What else it can do? right? So we are going to apply exactly that logic. You know, these things are mathematically very, just imagining that somebody actually thought about it, it's actually rather clever to show that it converges. So we will first show that pk we have to find out under what conditions these things happen. But if we can show that pk is less than or equal to some constant w for all k, and simultaneously show that pk plus 1 is greater than or equal to k, and also show that this limit will converge, then we will find that the matrix will actually converge to another matrix. I mean, of course, you will have to, you know, convergence of numbers are well defined. What do I mean by a matrix converging? I mean, a matrix converging in this case means that they will converge element wise. That is, the element p11 will actually converge to some constant number, p22 will converge to some number. So they will converge element by element to a constant matrix. So we have to find out under what conditions this happens. Then P will be LTI, then G will be LTI, then Kalman filter will be LTI. Okay. So first of all, first result is this, that if, you know, this is because I don't know whether any of you wondered that in the first lecture we talked about deterministic state estimation, where there was none of these stochastic noise, etc. And as we know that in a deterministic system, state can be estimated only if the system is observable. Otherwise, how can you estimate the system? Now here we are having an estimator, okay, stochastic, but still we are trying to estimate the state in a same kind of model, but never talked about observability. Throughout the Kalman filter discussion, we have never talked about observability. So how is it that in one case, in both cases, we are trying to construct a state estimator, but in one case it is becoming, I mean observability is the key property. In a deterministic case, you cannot solve for the state unless the system is observable. You will get non-unique solution if you try to solve for x from a given set of measurements. But in the case of Kalman filter, we never even brought that concept. It never arose. So we will find that, so it is somewhat natural that somewhere it should come. It should play some role. So now we will find that observability and controllability are going to play roles. So first of all, we have the first result that if C and A are observable, then this matrix is bounded. After all, what does it mean? This means that what is this pk? This pk is the covariance of the estimation error. So it says that if the system is observable, then the estimation error does not grow beyond bound. Remember that we are not requiring that the original system is stable. A may be an unstable matrix, that we are not requiring. We are talking about the filter. Try to distinguish between the filter and the system. The system has state matrix A, and the filter has state matrix A into I minus GC, that we have shown. Filter is also a system. Okay. So here we are saying that if CA is observable, then the state estimation error does not grow unbounded. So it's good. We at least found an evidence that observability of the system helps in estimation, even in this case, just like it helps in the deterministic case, right? So how do we prove that? So the basic argument is these are, you know, rather clever, very clever algebraic manipulations. So what they are trying to say is that since the Kalman filter is a minimum variance estimator, so this estimation norm is going to be less than any other estimation norm that you have any other estimator you construct and put here, the corresponding estimation norm is going to be more than the estimation norm of this, because the Kalman filter is minimum variance. Okay, and then they will choose this estimator in such a manner that this thing becomes independent of k. So then this will become a constant matrix. So they will prove that there exists a constant matrix such that the Kalman filter pk will be less than that. That's all. That is all that you need to prove. So the whole idea is in a very tricky manner choose this estimator x star k, and you can choose it when the system is observable. That's how observability comes in. So you can show that you can construct some x star k in a clever manner such that if the system is observable, then this whole expression becomes a constant matrix W. That is the way it is proved. It has a lot of manipulations. So it turns out, so first result is that so we have found that if CA is observable, then that roof we have established. PK cannot go beyond that. Okay. So now the next one. So now we say, for example, we have, let us define this right hand side of this thing is we call psi pk minus 1. There is this function is we are calling psi. Just giving it a name. This right hand side function, it is a function of pk minus 1. We are calling it a function psi pk minus 1. If that happens, then there is another result that we want to prove, that if P is greater than or equal to Q, take any two matrices. Take a matrix P, take another matrix Q. If P is greater than Q, remember that every time remember that when we are saying P is greater than Q, we mean that for all x, x transpose Px greater than x transpose Qx. It's right. These are all positive semi-definite matrices. So x transpose Px is greater than or equal to 0 for all x, and x transpose Qx is also, so always, because greater or less about two matrices, how can you say? The matrix has many numbers. So whenever we say P is greater than or equal to Q, it is in that sense. Okay, this you must remember. So P greater than or equal to Q implies that psi of P is greater than or equal to psi of Q. In other words, the psi function is monotonic with P. If you take a greater P, you will get a greater psi. It's like log x. Okay, if x1 is greater than x2, log x1 is greater than log x2, like that. So now we can prove that. Now let us assume that P0 equal to 0, just arbitrarily. Actually P0 is not 0. If P0 is 0, then obviously P1 is greater than P0, because P1 is positive semi-definite, so it cannot be less than 0. All P matrices being symmetric are positive semi-definite matrices. Any symmetric matrix must be positive semi-definite. Okay, because it can be written as G transpose. So if it can be written as G transpose, then it cannot be, then it must be positive semi-definite. So this is positive semi-definite, therefore it is greater than or equal to P0, because P0 is 0. Correct? So this is another kind of proof. You know, we have seen proof by contradiction, we have seen proof by construction. This kind of proof is called proof by induction. So I have to prove that Pk plus 1 is greater than or equal to Pk for all k. So I am first showing the base case, that is, at least for k is equal to 0 it holds. Then I am showing that if for k is equal to 0 it holds, then for k is equal to 1 it holds, because P2 is equal to psi P1. See, the previous equation was left hand side was Pk, right hand side was Pk minus 1. So we had Pk is equal to psi Pk minus 1. That is the covariance update equation. So we have P2 is equal to psi P1. But since P1 is greater than P0, therefore psi P1 must be greater than psi P0. But then what is psi P0? Psi P0 is again P1. If P2 is psi P1, then P1 is psi P0. Correct? So P2 is greater than P1. So if P0 is greater than, if P1 is greater than P0, then P2 is greater than P1, it follows. So obviously now if P2 is greater than P1, then P3 will be greater than P2. So in this way we can go on, and then we can prove, in this way continuing, we can say that Pk plus 1 is greater than Pk. So now we have established both of them, that it is bounded but it is increasing, correct. So actually if okay, now if now we can now just to know that it will actually converge element wise, you can think about it like this. Imagine this number, for some vector y, take an arbitrary vector y, then y transpose py will be a number, it will be a scalar number. So if since pk is continuously increasing, so y trans for a given y transpose py is also increasing. After all, that is the definition. And how do we say that pk is increasing? If for a given vector y transpose py keeps on increasing, then only we say that pk is increasing. Okay. So this is an increasing sequence of numbers. So now we have come from matrix to number. So we have an increasing sequence of numbers which is bounded on the top because y transpose wy is constant. So therefore this number sequence must converge. There is no other way. Now I can now this should happen for any y. So now I can choose y to my wish. So first of all I choose y as a unit vector as 1 0 0 0 0. So if I choose y as 1, only first element 1 and all others are 0, then this y transpose pky will be what? It will be the first element p11 of the matrix P. Right? So now y transpose py convergence means what? Means p11 converges. So in this way we can prove that first if I choose y as the first element 1, all other 0, then I choose second element 1, all other 0, third element, so I can first prove that all the diagonal elements will converge. Then I can choose y as first element 1, second element 1. Then I will get p11 and p12. Now p11 has already converged, so therefore p12 will also converge. In this way we can prove that the whole matrix of y, whole matrix P will converge element wise. Nice, see how they are in steps here and there, they are gradually proving one thing or the other. That is rather nice. But what is the catch now? We have not yet reached our destination. The catch is here, that we assumed that P0 equal to 0. P0 is not 0. P0 is expectation x0 minus x0 bar into x0 minus x0 bar transpose. How can it be 0? So so this is not enough. We have to prove more. So the question is, when does pk tends to p with a positive symmetric non-zero p0? Positive semi-definite. When I say PSD, I mean positive semi-definite. When I say PSDS, I mean positive semi-definite symmetric. So this is the question that is of interest to me, because P0 is never going to be 0. So the answer is that if the filter is asymptotically stable, then it happens. This you can probably understand that P0 is 0 means P0 is like an initial condition, right? So for 0 initial condition we have proved that the matrix will converge. Because the elements are we have considered to be, I mean ABC we have considered time invariant, input properties V etc. we have considered time invariant. But when does the effect of initial condition die down in a system eventually? If the system is asymptotically stable, that we know that the initial condition response of any linear system dies down to 0 if the eigenvalues of the system are strictly within the unit circle in the discrete case, then only it will die down, no? So here also it will turn out that if the filter is asymptotically stable, then pk will tend to p. So how do you look at that? This is again a good amount of algebra, but interestingly it turns out that various reachability conditions etc. come out. Actually, we are trying to say that for arbitrary ABC, we are not requiring any condition of stability of asymptotic stability of the system. We are requiring asymptotic stability of the filter. So the system may be unstable. So if, and you can understand, I mean, if you, I'm just trying to relate these with various kinds of results. Look at this. This looks like a, somewhat looks like a pole placement result, no? A is the original matrix minus some AK, GK, CK. Pole placement closed loop matrix is what? Is A minus KC. If you have output feedback, here we are having output feedback. So this is somewhat like a closed loop system of, I mean, arising out of some pole placement in the estimator, and we are requiring that the estimator be stable, irrespective of the system being stable or unstable. So when can you stabilize by pole placement any system by state feedback? When the system is controllable. When the system is controllable, you can always find a gain K, which will give you a stable closed loop system. So obvious, now we are requiring that whatever is the original system, the filter should be stable. So obviously it seems natural that it should translate to the controllability of the A gamma matrix. In this case, B is gamma. Is it not? So this result is, it is not intuitively unnatural. So it will turn out, so first of all they will prove some technical result that if it converges, then P minus Pk is this. This is just put P is equal to that steady state solution. P minus Pk will be equal to psi P. They will write that P minus Pk is equal to psi P minus psi Pk minus 1. And then they will put, obviously P is equal to psi P, that is the steady state solution. We have already said that if a steady state solution exists, as it will, we have just now proved it, then that must satisfy P is equal to psi P. And normal matrix Riccati equation satisfies Pk equal to psi Pk minus 1. So obviously P minus Pk is equal to this. So if you just put psi and psi P and psi Pk minus 1, those functions, subtract and take common, do some manipulation, you will get this form. So now you see that gradually you will find that observability conditions we have already got in our analysis, in our steps of argument. Now we will start getting controllability conditions. The moment we will require that the filter converges for non-zero initial conditions, we will start getting controllability conditions because of this reason that I discussed. Then you will prove that if A gamma is reachable, reachable means what? That the actually controllable and reachable, you must be knowing that there is some technical difference. I mean, it is from origin case. I mean, if the A matrix is 0, then also it may be controllable. I mean, just imagine that if A and B are both 0, then in one step you can reach the origin. So reaching the origin is not a problem. Reaching the origin does not require that the matrix B, A, B, A to the power n minus 1 B, that matrix has rank n. Reaching the origin can be given for degenerate cases of systems. It is actually reaching an arbitrary point from the origin which is more important or more practical. So such things are called reachable. So basically, when I say this reachable, I mean that that corresponding matrix, that is gamma, A square gamma, A to the power n minus 1 gamma, that matrix should be full rank, as the standard result. I mean the controllability matrix. Then it can be shown that for all Pk will be continuously greater, not positive semi-definite. Pk will be positive definite for k greater than n plus 1. Wherever P0 you start, the whole sequence, if you start with a positive semi-definite symmetric P0, then after n plus 1 iterations, n is constant, n is the order of the system. All other Pk will be greater than 0. This is an intermediate result, not of much significance. Only thing is that, why I wrote it, it's actually a intermediate manipulation result, but why I wrote it is to just show you that the reachability condition is coming. Okay, then you can show that this by further manipulation, this is P minus Pk is equal to this into P minus Pk minus 1. So now you again say that P minus Pk minus 1, that is this one, you now expand. You can expand this. So you can continuously go on expanding this and then finally come to P minus Pn plus 1. So every time on the left hand side you will get another A into I minus Gc. So here you will get this term. Can you follow this? If P minus Pk is this, then again P minus Pk minus 1 will be another A into I minus Gc. Here I minus Gk minus 1c, and in between P minus Pk minus 2. In this way you can go on expanding. So this is on the left hand side, this is obviously bounded because P is a constant matrix, Pn plus 1 is again some constant matrix, and now this Pn plus 1 will actually depend on P0, obviously it will depend on P0, and this B, basically by B it's a long matrix, it is I minus Gk minus 1c into I minus Gk minus 2c into n and so on. So this is just a symbol. So what do I want? I want to know when Pk converges to P, even if there is a non-zero P0. Now I am working with non-zero P0s. Okay, so I want to know when will it happen. It will happen if this goes to 0. See, if this is going to 0, this is bounded. If I can prove that this is also bounded for arbitrary k, let k tend to infinity. So k tending to infinity means this will be something like x to the power k. See, k on the top, and this is like a number of things, that is I minus Gk minus 1. So it is also a product of infinite number of terms. So if this has to go to 0, then this, even if it is a product of infinite number of terms, it should be finite. If this is finite, and this goes to 0, then this goes to 0. That is true. Two finite numbers, just treat them as numbers to understand, right? So now it can be shown that if system is observable, then this is bounded. So they will step by step prove these results. And now this is obviously bounded because it is at a fixed point. It is at n plus 1. N is fixed. So you have started from P0. So within Pn plus 1 you cannot blow up. Okay. So this is a constant matrix. So this is bounded definitely. So that means that this will be 0, this is bounded, this is bounded. So this will be 0 only if this goes to 0. When will this goes to 0? When will a matrix A to the power k go to 0? When its eigenvalues are less than 1. It will contract, right? Any matrix A, if you take any vector Ax, this vector Ax is going to be bounded by lambda mean of A into x and lambda max of A into x. So the length of this vector is always going to be greater than lambda mean A. If you multiply, lambda mean is a number. If you multiply the original vector by lambda mean, if you multiply the original vector by lambda max, you will get two vectors of two different lengths, and this vector is always going to be somewhere in between. So the length of the vector by a linear transformation is always bounded between the minimum and the maximum eigenvalue. So if this has to contract, gradually shrink to 0, I am saying that as k goes, it will slowly shrink to 0 and P will converge to Pk. So then obviously it should have less than unity eigenvalues, which means that the system should be asymptotically stable. Filter should be asymptotically stable, not system. This is the state matrix of the filter. So now we have the now you can now prove also. Now how do you know that this has so So P will converge to Pk if this eigenvalue is less than 1. We don't yet know whether it is less than 1. But if it is less than 1, then even for non-zero P0, Pk will converge to P. And then finally you can prove that if A, C and gamma are controllable and observable, then this is less than 1. That is like a pole play. That means the Kalman filter by its optimizing algorithm always finds a state feedback gain K. See, the environment is such that there will exist a state feedback gain K, since it is controllable and observable. So this, and then the Kalman filter by its algorithm will always compute a gain K such that the closed loop system will be asymptotically, such that the filter will be asymptotically stable. I mean, if you see that the filter is like a closed loop, like something you obtain by state feedback from the closed loop system, from the open loop system. So finally we have arrived that Pk tends to P even with non-zero PSD. Filter is also asymptotically stable, obviously, and naturally P is independent of P0, because if the filter is stable, then the effect of P0 will die down. Asymptotic stability. So whatever initial state error P0 you start with, eventually Pk will convert to the same P, right? Now question is that, so after it converges, what does it show? It shows that after it converges, it acts like a stable filter. See, we have proved the stability of the converged filter. Okay. So in fact the time varying filter is, you can also prove with lot of manipulations. I do not know how exactly, I have not read that proof. That the time varying filter is also asymptotically time invariant and stable. Then you can do the analysis actually for the time varying filter for stability. That will be a much more complicated thing. So I think we have 5 minutes time, and these two topics are very simple. So you have to just understand the concept. So now we want to see that if you have colored noise, what do you mean by colored noise? Colored noise means that expectation of xi k xi l transpose is equal to q k l delta k l. This is an assumption that we made, that the process noise sequence itself is uncorrelated with its own samples. That assumption is I am not assuming anymore. So I am assuming that now xi k is rather generated in this fashion. So obviously xi k and xi k minus 1 are correlated, because xi k is generated from xi k minus 1. But now I am assuming that this is a sequence which satisfies this property. This is an uncorrelated sequence which I am feeding through a filter to get xi. So the process noise sequence is correlated, but it is modeled as the output of a linear filter, time linear filter, whose input is a white sequence. That is a standard way of modeling correlated sequences, because we have seen in the previous thing that if you have any correlation pattern or if you have any power spectral density, you can always do spectral factorization and then assume that has been generated by a white input coming to a filter. So here also we are assuming that the xi k, which is correlated with itself, autocorrelated, is generated from a white sequence through a filter. That is a very standard way of modeling correlated sequences, and eta k is similarly being generated like this. So now what is the optimal filter? Because our assumption is gone. So then how do we make an optimal filter, minimum variance? So that is, I mean, the approach is very simple. The approach says that just model this also as part of the system. So now your state vector will become previous state vector plus xi k. That is as if xi k is also a state. Yeah, you assume like that. So you augment the state vector. So now you write the update equations for xk and xi k both. So the update equation for xk is the old one, ak gamma k, and for xi k is this one, so mk. So now this becomes your state matrix, new corresponding to this state the state matrix, and this will become your input matrix. So now you have defined an augmented system, first one containing the original system, then the containing the noise dynamics, that also you are trying to estimate. So now your overall augmented state equation is this, correct? And interestingly, this satisfies Kalman filter assumptions, because this has, what does it have? It has 0 BK, is a new process noise sequence. In this, so the vector is still, so the vector is still 0 mean, because this is 0 mean and this is 0. What is its variance? For these components, variance is 0. For these components, it is still white. So this is also a white sequence. So this obeys the original Kalman filtering forms, right? Only the output equation is a bit of a problem. So yeah, and you can easily write the output equation again in this form. So finally you can get an, you have to define a new output, which is Vk minus 1 minus Nk minus 1 into Vk minus 1. So now two outputs, but finally you will get the output equation in this form, which is again our old form, because here this is our output, equivalent output, this can be computed, this is Vk. So at V dash k, Vk is known, so therefore this can be computed. So it is an equivalent measurement. So now your new measurement equation is this, with a new matrix, state and gamma k, which is again a white sequence. So with this state equation and this measurement equation, these two are in the normal Kalman filter form. So you can estimate the Kalman filter for these two, right? That will give you the optimal filter. From there if you take the top part, you will get the state. So the trick is simple. Trick is to define an augmented system, model the noise dynamics also within the system dynamics, right? And lastly, if what happens if correlated state and measurement noise. So I am assuming, in this case this correlation can occur with some delays also, but I am assuming that this is the most common case, that xi k and eta L are now correlated. Previously what was my assumption? That xi k and eta L is equal to 0 for all k and L. Even if this is k, this is k, because these are different, it is 0. That was my assumption. Now I am assuming that if this is k and this is k, then it is non-zero. It is UKL delta KL. So at same instant, xi k and eta k are correlated. Okay. So then again I have to rewrite the system equations. I have to do some clever transformation such that the transformed system has, all those nice properties of previous Kalman filter maintained. So what I am doing is I am writing this transform system. I am writing a new state equation. Why this is correct? Because this equation is identically 0. See, zk equal to ck xk plus eta k, na? Zk is vk actually. I have written from a different book, so my notation has got changed. This is vk. Vk is equal to ck xk plus eta k. So that means this term is identically 0. So I can always add it. Okay. Then I am rearranging terms. So this tk, ck, xk, I am put it here. I have this term and I have this term. Now you see that interestingly, this term is known because zk is a measurement. So it is like a known input case. Previously even for Kalman filters we can have known input and we can have unknown input. The unknown input we had assumed to be random. Known input is fine. Known input will again partition the state. So this is like a known input. This is like the new noise, process noise. Now the new process noise is xi k minus tk eta k. This is my new process noise in this transform system. Now, so I have to choose, now I have to ensure nice properties of this by choosing this tk appropriately. So now what is my condition? That choose tk such that this must be equal to 0. That is, the expectation of this is 0. That is obvious. But expectation of this I am calling as xi star k. Okay. So this is the new process noise. Now I want that tk should be such that the new process noise and the measurement noise should now be uncorrelated. I started with the assumption that process noise and measurement noise are correlated. I have now defined a new process noise, and I must define this process noise in such a manner that this becomes uncorrelated. So I will now put what is this equal to this, and then I will simply solve now what is xi k eta k transpose, that is uk, and what is eta k transpose, that is rk. So I want this to be 0, so I will choose Tk is equal to uk rk inverse, that will make it 0. So if I choose such a Tk and then if I write this thing, again I have a new state equation in which I have a new state matrix, I have a new noise sequence which is uncorrelated with the measurement noise sequence, and I have a known input. Known input I know how to handle. So I can now write for this system and the old measurement equation Ckxk, I can write the Kalman filter. So that is all today. So we have seen an important property of time invariance, and we have seen two of the common cases, because these assumptions have to be sometimes assumptions appear restrictive, but it turns out that in many cases we indeed have by manipulation, by some augmentation, by some transformation, we can define an equivalent problem on which we can define a Kalman filter. So thank you very much.